Good evening, our listeners, and welcome to our today's class. Today, we are still continuing to look at the concept of a statistical test of a hypothesis. In one of our previous classes, we already had spent time giving elaborate introduction around the concept of a statistical test of a hypothesis. Of course, in the statistical test of hypothesis in our previous class, we stated or we said that it is just a test that is concerned with making a choice or making a decision about two competing or contrasting hypotheses, which of course is the null and the alternate hypothesis. In the class, we equally enumerated various tests that we'll be looking at in this statistical test of hypothesis, depending on if our sample sizes are large or whether they are small. And one of the tests which we enumerated included the test concerning one population proportion. So today we'll be looking at in detail the test concerning one population proportion. Of course, when we talk about one population proportion, we are talking about collection of items in totality that is looked at as an entity. And then this an entity now, of course, is what we regard to be one population. And when we talk about a proportion, we are talking about a ratio of the characteristics that exist in the what in the population. For instance, if you consider a manufacturer that produces goods and commodities or produces what commodities, and each of these commodities can either be defective or non-defective. It means that the population exhibits binary characteristics. It can either be this or it can be that. And of course, the manufacturer can make a claim or a hypothesis about the proportion or about the proportion of defective items in that product. He can come out and say that the proportion of defective item in his product is, for instance, 3 over 5. It is a claim. And this claim, of course, is regarded as a null hypothesis. So he comes out and says that H subscript 0, which we call the null hypothesis, that what pi equals what 3 over 5. This pi is used to represent population proportion. Now, this is a claim that is made by a manufacturer. So for someone to go into this particular test, to be able to agree or disagree with the manufacturer, one has to come up with what is called an alternate hypothesis, which of course is any hypothesis that contradicts the null hypothesis. And then the alternate hypothesis could be in any of the following forms. It could be that the person is saying that H subscript 1, that pi is not equals 3 over 5. This is what an alternate hypothesis. It contradicts the sign of the null hypothesis. Or the person can say H subscript 1, that pi is less than what 3 over 5. It's also a alternate hypothesis because the sign contradicts the sign of the the null hypothesis. Or it can be H subscript 1, that pi is greater than what 3 over 5. It is also an alternate hypothesis because the sign contradicts the sign of the null hypothesis. So in each time the person will be conducting a test, is either the person goes with this null hypothesis and this very alternate hypothesis, or the person goes with this null and this particular alternate hypothesis, or the person goes with this and this particular null hypothesis. So in a test, it is always two hypotheses that is involved, one particular or what the null hypothesis and one particular alternate hypothesis. That can be the two-tailed, it can be the one-tailed to the left, or it can be the one-tailed to the right. And we are making use of this 3 over 5 does not mean that it is conventional. It is just a choice that I mentioned that the manufacturer might be seeing that the proportion is 3 over 5. It could be another thing, and because it could be another thing, it is better to use something that looks like a variable to define it, such that the value can change into something else, assuming it is not 3 over 5. So this hypothesis stated in this way can equally be stated in its alternative form as saying that h subscript 0, that pi equals what? Pi 0. Where this pi 0 could be 3 over 5, or it could be any other number aside from 3 over 5. In that case, the alternate hypothesis now become this way, that h subscript 1 in relation with this, that pi is not equals pi 0. Or it becomes h subscript 1 that pi is less than what? Pi 0. Or it becomes in relation with this h subscript 1 that pi is greater than what? Pi 0. These and these are the same, only that here we are specific about the value of pi 0. And here pi 0 is not specified, and therefore it can take any particular value. That is the first thing that we need to do each time we want to conduct any particular test, that we must first of all state the hypothesis, which includes the null and the alternate hypothesis. That is the first thing we are going to do. Then the second thing we are going to do is this, or before that second thing, of course, another thing you need to consider is this. When the person must have defined the null and the alternate hypothesis, the person goes ahead to define what we call the level of significance. So in that number 2, we talk about level of significance. Level of what? Significance. Let me shorten significant as SIG, and it's always denoted as what? As alpha. We define this level of significance as the probability of rejecting a true null hypothesis. So it is an error, it's a mistake. The probability of the mistake one makes when one rejects a null hypothesis that is what? True. That is what we call level of significance. And because it is a mistake, the probability of a mistake in a test should be kept as small as what? As ever. And that's why oftentimes the value of this level of significance is always either 0.01 or 0.05, depending on the field of research. So it's always taken as what? 0.01 or 0.05. In the previous class, I already had stated that 0.01 is often used in medical researches, or what we call in health researches or health field, while 0.0105 is always used in in social sciences. That is the second thing one needs to do when you are carrying out tests about statistical hypothesis. Then the third step is now going to be to state the test statistic. To state the what? The test statistic. That is number 3 thing we are going to do. State the what? Test what? Statistic. And before we define this test statistic, let us go back now to the beginning of what this test. The moment the person now defines the null hypothesis and equally defines the alternate hypothesis, one goes ahead to take a sample from that population. And once one takes a sample from that population now, one is going to estimate what is called what? The sample proportion. Remember that pi here stands for the population proportion, which is the claim that the manufacturer made about the proportion that exists in the population of his product now that he manufactured. So you are going to go to this product that he manufactured now, take a sample from that product now, and then from the sample you have taken now, you'll be able to estimate what we call the sample proportion. And that sample proportion is often denoted with what? With a letter what? P. And then it's denoted with a letter P, and it is defined as what? X all over what? N. In the context of this either defective or non-defective item we are looking at, X stands for the number of defective items that is found in the sample, while N stands to be what we call our sample size. So while pi is the population proportion, P is talking about the sample proportion. And we are told that when this N is large, which is in statistics N greater than or equal to what? 30. That this P follows a normal distribution, which means that this P follows a normal distribution. And it is the parameters of that normal distribution is specified as what? Pi, comma, pi into 1 minus what? Pi all over what? Pi, close up. So it follows a normal distribution. And that permits me to remove something that came on front of my phone. So it follows a normal distribution with mean pi and variance pi into 1 minus pi all over pi. So for us to state the test statistic, which is of course is a function that is going to transform our sample observation into a numerical value, we are going to specify it now in connection with this what? With this P. And we have been told that P follows this particular distribution when n is what? Is large. And when n is large, the traditional test that is always used is what we call z-test, to test the significance of a population proportion. So, and of course, when you talk about a z-test or you talk about what? A z-score, you are talking about a standardized score. And to standardize a random variable is, if we have a random variable x, and this random variable x follows a normal distribution with mean, mu, and variance, sigma square. For you to standardize this random variable x, is going to be what? X minus what? Mu all over sigma, where this sigma is the standard deviation. So I am equally now going to standardize the value of this P, in as much as this test statistics now is going to be a standardized score, because we call it the z-score. So it is now going to be that the test statistics now is going to be what? Z, and permit me to be putting z car equals. I will come here now what? Now to be what? P, just like what I had x here, minus. What I had here was what? Mu, which is the population parameter. And in this case now we are discussing what? Pi. So I will now say minus pi 0 all over. What I have here is sigma, which is the standard deviation of this variance here. And the variance of this P is equally this. But I am now discussing pi in relation with what? Pi 0. So it is now going to be square root of, I have what? Pi 0 into 1 minus what? Pi 0 all over what? N. So here is here is all over n. So this is now what we call the test what? Statistic. And we are told that it follows what? Normal distribution with mean 0 and variance 1. This is what we call a test statistic. And of course, we are told that this test statistic, of course, is a decision maker. A decision maker in the sense that when the value of this test statistics falls into the critical region, we are going to reject the null hypothesis. But when it falls into the acceptance region, we are going to what? To accept the null hypothesis. So first of all, we are going to go into step 4 to tell ourselves that we are going to define the critical region. It's when we define the critical region now that we are now going to come back now and explain how this test statistic is regarded as a decision maker. So permit me to clean this place. Okay, the step 4 of carrying out that test is what we call that we are going to define or state the critical region. State the what? The critical region. State the critical region. The critical region. And of course, this critical region is going to be stated in connection with the alternate hypothesis. With the alternate what? Hypothesis. So, of course, when I have a hypothesis this way, that H substitute 0 that pi equals what? Pi 0. Against alternative or verse h subscript 1 that pi is not equals pi 0. We call this two-tailed what? Test. And when this happens, the critical region is going to be the absolute value of z car greater than what? Z of alpha over what? 2. Reject H0. Therefore, when we calculate the value of our test statistic, we obtain its absolute value and compare it with the z tabulated. When this absolute value of z cal happens to be greater than the z tabulated of alpha over 2, we are going to reject null hypothesis. Only when the alternative hypothesis is in form of a two-tailed test. Or when we have h subscript 0, that pi equals what? Pi 0 verse. That we have h subscript 1, that pi is greater than what? Pi 0. We are only going to reject the null hypothesis if this thing happens in connection with our z calculated and z tabulated. That our z cal happens to be greater than what? Z of alpha. In this case, alpha is not divided by 2 because it is one-tailed. Here, we are distributing the critical region what? In two sides. Because the critical region of a two-tailed test exists in both directions. We are going to give little illustration about that. But then, when we have something like this, that h subscript 0, that pi equals what? Pi 0 verse. That h subscript 1, that pi is less than what? Pi 0. We are only going to reject the null hypothesis if this thing happens. That our z car is less than minus z of what? Of alpha. So these are the conditions of the critical region depending on the tails of what? Of the alternate hypothesis. This one happens for two-tailed tests, two-directional. This one happens for one tail to the right, and this one happens for one tail to the what? To the left. Of course, when we talk about critical region, which we are defining, we are talking about the set of the possible values of the test statistic that will lead us into rejecting the null hypothesis. That's exactly what we mentioned that thing to be. So the fourth or the fifth step, which one we are going to consider is now the fifth step, which we are going to consider, which is number what? 5, is going to be what we call make a decision and conclusion. Make a decision and conclusion. So make decision / conclusion. And what we call making a decision / conclusion is having computed the value of the test statistic and comparing it with what the value of the tabulated, one will be able to make a decision that, okay, because the value of the test statistics lies within the critical region, we are going to reject the null hypothesis, and then disagree with the manufacturer that the proportion of the defective item is either 3/5 or either anything. These are the 5 necessary steps that one used to follow when you are carrying out the test concerning one population proportion. The use of this word, the critical region, acceptance region, is a popular thing in the test of hypothesis, and oftentimes it might be confusing. So we are going to use a little thing to showcase what we mean by critical region and what we mean by acceptance region. It's just an illustration that can give us an idea of what truly this critical and acceptance region is. So permit me to clean this. So we talk about what we call the critical region and then the acceptance region. Critical region and acceptance region. critical region, otherwise called rejection region, and then what we call acceptance region. This time around, we are talking about proportion. So I'm going to give that illustration now in relation to what? To proportion. Proportion, of course, is a probability value, and it lies between 0 and 1, inclusive. So I can give something like a line this way, and then I have something like this and something like this. Here is my 0, here is my what? My 1. For instance, that manufacturer made a claim, and the claim that manufacturer made is that the proportion of defective item in his commodity or in his product is 1/2, which is 0.5. Then you are now going to come at the center of this and you have something like what? 0.5. Now, you are now going to define what is called the critical region. And for instance, the hypothesis we are testing is H subscript 0, that pi equals what? 0.5 as this. Against the alternative that H subscript what? 1, that pi is less than 0.5. This is what you are testing. So you are going to define a critical region. And a critical region means a set of possible values of test statistic that can lead you into rejecting the null hypothesis. And if you come here, we are now going one directional. So we are somewhere from here down here. And of course, a value that is very, very close to 0.5 might not be rejected because they are also very close to this 0.5. So there might not be any significant difference between them. So you can come and have a line here now and possibly have here to be what? 0.45. And you are telling yourself that any value that falls between 0 to 0.5, you are going to reject it. Or you are going to what? To accept it. Then that any value that falls between 0.45 to this is of course very, very close to what? 0.5. That in that case now, you are not going to reject this claim that this person made here. So, meaning that in that context, from 0 to 0.45 now is what you are defining here now to be your critical region. And then from this your 0.45 to this 0.5 now is what you are defining as your acceptance region. Then you now go ahead now and calculate the value of your test statistic. If the value of your test statistics now falls between 0 to 0.45, you reject your what? Your H0. But if your value now falls between 0.45 and 0.5 now, you go ahead now to accept your what? Your H0. This is a kind of illustration, not necessarily that you are going to be using 0.45 and 0.5. And because we are talking about one-third test to the what? To the left, don't you see that the critical region lies what? At the left. But then if you are talking about something like what? You are talking about what? H subscript what? 0, that pi equals 0.5. Against the alternative H subscript 1, that pi is greater than 0.5. In that case, you might come here and make a line and you have 0.55. This 0.55 now, of course, or let me say 0.54. This value now is very close to what? To this 0.5. No much difference between this and this. So for you to say there is a significant value that is going to make this in actuality to be greater than 0.5, you are going to say let it lie between 0.54 and what? And 1. And in that case, here becomes your critical region. And from this 0.5 to 0.54 now becomes what you call your acceptance region. Therefore, if you calculate the value of the test statistic and it lies between 0.54 and 1, you are going to what? To reject the null hypothesis. But if it now lies between 0.5 and 0.8 now, you end up going to accept the null hypothesis. This, of course, is what we call the critical region and the acceptance region. And if you look in this context, of course, because we are discussing one tail to the right, of course, the critical region lies at one side. And that's the reason why oftentimes you hear people ask you, in a one-tailed test, the critical region lies at which direction? Either in one direction or in both directions. Or they will ask you, in one-tailed test to the left, where is the position of the critical region? Is it either in the right or either in the left? We have seen all of these things here. When it is one-tailed to the left, the critical region lies in the left. When it is one-tailed to the right, the critical region lies in the right. Equally with the acceptance region. They lie in that particular direction. But then when we are talking about h subscript 0, that pi equals 0.5 against the alternative h subscript 1, that pi is not equals 0.5. In this case now, this pi is allowed to move in both directions. So we might just come here and use either 0.44 and then 0.54. Any value that is going to fall between this 0.44 and this 0.5 now, of course, are values that are close to 0.5. But any value that falls now between this 0.5 and 0.54 are equally values that are very close to 0.5. So, but any value that falls between this 0 and 0.44 now are values that you consider being far away from this 0.5. And in that case now, from here to here is looked at as what we call the critical region. And this value from here to here are equally far away from 0.5. And then this place equally becomes a critical region. So when the value of the test statistic falls here, you reject the null hypothesis. If it falls here, you reject the null hypothesis. But if it falls between here now, you now accept the null hypothesis. So here critical region, here critical region. So in the two-tailed test now, the critical region lies in the two directions. While here is the position of the acceptance region. So permit me to clean. Of course, when we talk about z of alpha, we talk about what z of alpha. We are talking about a value that locates this alpha at the tail of a standard normal distribution. A standard normal distribution. So, if I want to represent in the right way, the critical region of a two-tailed test, I am going to use a bell-shaped curve of a standard normal distribution. And in that case, you see them drawing something like this. You draw something like this, draw something like this. Then you have a value from here to here. Then you might have something here to be 0. So here now you have a value here and you have a value here. So here and here are the critical region. You have alpha over 2, you have alpha over 2. This thing is now for the two-tailed test, where the value of the critical regions exist in both directions. But when you have something like this, and you have something like this, then you have something like this, the center, 0, and you have something like this. Then you have alpha. Then it is the critical region for one-tailed test to the right. Sorry, to the left. But when you have something like this, and then something of this kind, then you have something like this at the center, 0. You have something like this. You shade here, and here becomes alpha. Here now, of course, is the critical region at the tail of this standard normal distribution, but to the right. So it is actually called a one-tailed test to the right. That is the critical region of the one-tailed test to the right. So when they give you this kind of diagram and they are asking you what kind of a test does these critical regions now represent, you represent for the two-tailed test, you represent for the one-tailed to the left, and you represent for the one-tailed test to the right. I want to believe that this illustration must have given you little idea of what we call the critical region or rejection region, and then the acceptance region of a test of a hypothesis as it concerns Z tests. Thank you very much. We are now going to take one example and then look at that example holistically, how to compute it and the rest of them. So permit me to clean here while we solve the question together, following the steps that we have enumerated. Okay, let us write the question down on the board. Now this question says, let us read it together. This question says, that is question number, I call it solve problems. Solve problems. Number one. That number one says, a manufacturer of a certain product claims that 90% of his products are non-defective. 90% of his products are non-defective. Therefore, this manufacturer produces commodity that can be classified either as defective or non-defective. And he is saying that 90% of his products are non-defective. So we talk about for the non-defective 90%. Non-defective, non-defective equals what? 90%. Okay? And of course, you know quite alright that this 90% means what? 90 all over 100, which becomes what? 9 all over what? 9 all over 10, which becomes, yes, 9 all over what? All over 10. Then we read on. In a random sample of 160 products. So somebody wants to carry out a test on this. He has gone to the product of the manufacturer. He has taken 160 items or products, which means my N equals 160. So I have that my N equals what? 160, where this N is the sample size. Then he said in a random sample of 160 products, only 140 is non-defective. So from this 160 that was taken, only 140 is non-defective. So non-defective from the sample, non-defective equals what? 140. Okay? They said test this claim against the alternative hypothesis that the percentage of the non-defective is lower than 90. Test it that it is lower than what? 90. We are going to test this against the alternative that it is lower than what? 90%. At alpha equals 0.01. And they gave us something. They asked us hint. They say hint that our z-cal equals 2.326. And then our z-tab, tab. But they say that our z-tab, which is our z-alpha, is this, and our z-cal equals minus 1.054. That's what they gave us. Z this and Z that. That is the value which they gave us. Minus 1.054. So what we are going to do now is to go into the test proper and be able to know whether what they have there is going to be right or whether what they have there is going to be wrong. So we are going to go into the test one by one, starting with the stating of the hypothesis. So I will come here. I will write solution. We are going to begin by stating the hypothesis. The hypothesis here is that H subscript to 0 that pi equals what? 0.9, or what we call 9/10. 9/10. They ask us to test it against the alternative that is less than 90. So I have against h subscript 1 that pi is less than what? 9/10. This is my null and this is my alternate hypothesis. Now we go ahead now, second step, to state the level of what? Of the significance. And level of significance is what? Is alpha. Alpha equals, they gave us alpha to be 0.01. So this equals 0.01. The third step says we are going to state what we call the test statistic. And our test statistics now, our z-cal equals, we have what? What we call p minus, what we have what? Pi 0 all over square root of what? Pi 0 into 1 minus what? Pi 0 all over what? N. All over n. And we are told that this thing follows normal with mean 0 and variance 1. So we are now going to now first of all obtain the value of our p, because we know the value of our what? Of our pi 0 is given as a 9/10. So I'll now clean this top to be able to see what we are doing clearly. I'll clean this top. We should be remembering that this is 0.9 or 9/10. So I want to obtain the value of our p. We now say, but my p equals what? X over n. Where in this context, x stands for the non-defective items, while n stands for the number of samples. The number of defective items is what? Is 140. Non-defective item is 140. And the sample size is what? Is 160. So this thing becomes what we call 140 all over what? 160. And in that case now, this is gone and this is gone. I have 14/16. Then 2 here is what? 7. And 2 here is what? Is 8. So I have a 7/8. So when I have 7/8 now, I've got the value of my what? Of my p. I'll now come and substitute everything into this place. And by that substitution, what I have now becomes, permit me to clean here. So what I have now becomes that my z-cal now equals, in place of p now, I am going to write what? 7/8 minus. In place of pi 0 now, I am going to write what? 9/10. Then all over, I have square root. Pi 0 is what? 9/10 into, here is what? 1 minus what? 9/10. Then all over, here is my what? 160. Because n is what? Is 160. And of course, they told us that the value of this, that hint they gave us, they say hint that our z-cal equals 1.054. Is given as 1.054. So we now have that this equals minus 1.054. That's the value. So you can try to see whether you can put the values, use a calculator to be able to know whether you are going to evaluate something that is close to this or is this. So this is the value of our test statistic. And they equally gave us our hint that our z of alpha is given as 2.326. That's the value they gave us. So we now remember that our critical region is, for this particular one tail to the left, our critical region is that z-cal less than minus z of what? Alpha. We are going to reject what? H0. So the question is, what is our z-cal? Our z-cal is this. So our z-cal becomes what? minus 1.054 less than. Here is minus minus. Z alpha they gave us is what? Is 2.326. We now see, is this value less than this value? The thing there is what? No. This value is not less than. This value happens to be greater than this particular value. So in this context, we are not going to reject what? Our H0. Because we have found out that this value is actually less than this value. Okay? So that is how that one goes. So I want to give you something like a classwork for you to try. So try this question at your convenience. I called it here classwork. And that classwork says, a director of a given government parastatal said that 70% of the employer are men. In a random sample of 184 employers, 135 are men. Test this statement against the alternative hypothesis that the percentage of men is not equals 70% at alpha equals 0.05. I repeat the question so that you can take it down very much well. I say, a manufacturer, no, I said, a director of a given government parastatal said that the 70% of employers are men. In a random sample of 184 employers, 135 are men. Test this statement against the alternative that the percentage of men is not equals 70% at alpha equals 0.05. Whatever thing that your answer becomes, you can drop it on the comment section for us to see and know whether is correct or whether it is not correct. Thank you very much, as we are going to go over to two sample tests of proportion or two population proportions. So permit me to clean this one. The example we looked at only considered one population and one proportion of defective items. So we are going to go over to another kind of test. And that kind of test is talking about test concerning the difference of two population proportions. Test concerning the difference between two population proportions. So in this case, we are looking at two separate populations altogether. That is either manufacturer A and manufacturer B. And this manufacturer A and manufacturer B are competing or are in competition. And people are making a claim that the proportion of defective item in manufacturer A is equals the proportion of defective item in manufacturer what? B. So in this case now, we are being confronted by two population proportion. The proportion coming from manufacturer A, which is looked at as an entity, as a population. The proportion coming from manufacturer B, which is looked at as an entity, as a population. Which means in that case, I am going to have what we call pi 1 and what we call pi 2. Pi 1, the proportion coming from manufacturer A, pi 2, the proportion coming from a manufacturer B. Of course, I can equally write it now to be what? Pi A and what? Pi B. And someone is making, and they are making a claim that there is no difference between the proportion of defective items in manufacturer A and manufacturer what, B. If they say there is no difference, the implication there is that pi A minus pi B will always be what? Be 0. That is the implication. So which means that that hypothesis becomes that H subscript 0, that pi A equals what? Pi B. And this is the same thing like writing that pi H subscript 0, that pi A minus what? Pi B equals what? 0. But it might not necessarily be 0 at times. So you see them using something like delta 0, that the change is very close to what? To 0. That's what they mean by delta 0. So you can see them stating something like this, that H subscript 0, that pi A minus what? Pi what? B minus what? Delta 0. Or what they say equals what? Delta what? 0. And of course, this thing you have here can be written as this, that this is H subscript 0, that pi what A minus what? Pi what B is equals what? Delta 0, which is exactly what I have here anyway. This thing becomes what? The null hypothesis. And this delta 0 is, of course, a change, a small change, very small change. It can be 0 at times. So that this minus this thing becomes 0. So, which means if somebody comes up with this kind of what? Null hypothesis, which is a claim, we are going to formulate the possible alternate hypothesis to be able to test this claim. And formulating it now, the alternate hypothesis is going to exist in one of these formats. You are going to say against H subscript 1 that pi what A minus what? Pi what B is not equals delta 0. Or you are going to say that H subscript 1 that pi A minus what? Pi what B is less than what? Delta what? 0. Or you are going to say that H subscript 1 that pi what A minus what? Pi what B is greater than what? Delta what? 0. These are the possible alternate hypotheses that one can easily use to compare or to test this null hypothesis. This is what we call the hypothesis for two population proportions. The next thing, of course, becomes that we are going to state the level of significance. And without wasting time here, this thing becomes our 1 and this thing becomes our 2. The level of hypothesis, of course, is going to be what? Is going to be alpha equals 0.01 or 0.05, depending on what you are given. So you have done that. Then we now move to what we call the third stage. And then that third stage is now going to be that we are going to define what we call the test statistic. Define what we call the test statistic. And of course, we know that test statistic is a function. So, and before one goes into this test proper, when someone must have made this a claim, you are going to take a sample from population A and you are going to take a sample from population B. Therefore, you are going to have what we call NA and what we call NB. Sample coming from manufacturer A or population A, sample coming from manufacturer B or population what? B. And from these samples which you have taken, you are going to calculate what we call the sample proportion from A and the sample proportion from what? From B. So I can decide to call it now that you are going to calculate what? P of what? A and calculate what? P of what? Of B. And then, of course, when you talk about P of A now, to calculate this one, you are going to say that your P of A is going to be given as what? X all over what? N of what? A. And then your P of what? Of B is going to be given as X all over N of what? Of B. That is to say, from the sample you have taken from population A, you are going to count the number of what? Defective item there and divide it with the sample size. And that becomes the proportion of defective item in population A or in product of a manufacturer A. Equally, you are going to come here, count the number of defective items from this sample taken from a manufacturer B all over the sample size. So you have gotten what is called your PA and then your PB. So we now go ahead now to define our test statistics. But then, of course, we know that we have been told that when our n is large, n greater than or equal to 30, that this our PA, you are seeing here, that this our P subscript A follows a normal distribution with parameters pi of A, which is of course what we are talking about here. Then you now come here and say pi of A into 1 minus pi of A all over. You now have what we call n of A. Then, and this our P of B follows normal with parameters pi of B, then pi of B into 1 minus pi of B all over n of B. So these are the possible, the distribution which they follow when this n is large. And because we are talking about n being large, we are equally going to use our z test, which means we are going to consider what we call the z score or the z value. And when you talk about the z value or the z score, you are talking about the standardized value. And in this context now, we are going to talk about the difference between the population proportions or the difference between the sample proportion. So we are already taking the difference. And then our test statistics now becomes in that context. So permit me to clean here, believing that you have seen how we can state our hypothesis. Then I'll clean here. So our test statistics is now going to be, I am now going to have what we call my z-cal equals. Then I'll have what we call my P of A minus my P of B minus delta 0. This delta 0 is always there 0, such that this thing can easily be written at times as P of A minus P of B. Then now say all over. You have something like this. Of course, it is going to be, for us to standardize now, we are going to divide with the square root of of the variance of this and then the variance of this. That's what we are going to do. So which means I'm going to say all over the square root of we have here am I now? I'm having pi of A into 1 minus pi of A all over n of A plus. Here am I. I have pi of B into 1 minus pi of B all over n of B. We are told that this follows a normal distribution with mean 0 and variance 1. This is what we call our test statistic. Our test statistic. But then, if you watch very much well, most of the time, we are not told the value of our pi of A and pi of B. Someone just comes and says that the proportion of defective items in population A and population B are the same. And we go ahead now to carry out that test without not necessarily knowing the true value of this pi of A, pi of B. That's why they will always tell you that their values are always unknown. And because their values are always unknown, we are going to estimate it. And when we want to estimate it now, we are going to estimate it now using what we call the sample proportions. But the estimation is done under two conditions. The first condition is when we assume that the proportion of a defective in a population A is equal, is the same as the proportion in the proportion of defective items in population B. So in that case, in that assumption number 1, we are assuming that pi of A equals pi of B equals pi. What we mean by equals pi is that if this is 1 over 2, this is equals 1 over 2, which is 1 over 2. That is one of the assumptions. And we are told that if this thing happens, that we are going to estimate this pi of A and pi of B with what we call P bar. equals. We have what we call n of what A, P of what A, plus n of what of B, P of what of B, all over n of what A plus what n of what of B. We are told that if this thing happens, this is what we are going to use to estimate it. But then, before we now tell ourselves how this is going to be, we are going to return to this formula now to see what is going to happen here now when we assume that this and this are equal. Because that's the claim we made here, that this and this are what? Equal. If this and this are equal, it means that anywhere I see this, I will put pi there. Anywhere I see this, I will put pi here. And then this thing becomes, this zcal becomes that my zcal equals, here is my what? P of A minus what? P of what? B minus delta what? 0. This is delta 0. Then I have all over. Here I have general square root. Here now, instead of writing pi of A, I'm going to write ordinary pi. So I have pi into. Here becomes 1 minus what? Pi all over what? N of what? Of A plus. Here becomes what? Pi, instead of writing pi B, into 1 minus what? Pi all over what? N of what? Of B. This thing becomes in this format. And of course, when this thing becomes in this format, we can decide to look at what we have inside. We can decide now to solve what we have inside here, inside this square root. And solving what we have inside this square root now, what I'm going to have here becomes, what I'm going to have there becomes, what's the LCM of n of A, n of B? The LCM of n of A, n of B is n of A, n of B. That is n A, n B. So I'll have something like this. I want to solve what is under first. Then I'll come here. I have what we call n A, n B. Then I'll come here and see this place now. Now, of course, like what we have said before, this and this are now what? Equal. And this are now what? Equal. So they are the same values. Because they are the same values now, what I'm now going to do now is now to come here. Once I write n of A, n of B now, I'll come here and see. N of A divided by this is n of B. So I have n of B multiplying the whole of this. N of B multiplying the whole of this. So I have what? N of what? Of B into. I have what? Pi. I have what? Pi into 1 minus what? Pi, which is what I have in this place. Then I will say this one, this quantity divided by this will give me n of A. So I have what? Plus, we have n of what? Of A, then pi into what? Pi into 1 minus pi. Close the what? The bracket. Of course, there is pi into 1 minus pi here. There is pi into 1 minus what? Pi here. These places. So I can easily now bring it what? Outside. I'm bringing it outside now. What is now going to happen here becomes what? That I have what? I have pi into 1 minus what? Pi. Then I'll open a bracket. What is remaining here is what? N of what? B plus what? N of what? Of A. Then all over what? N of what? A, N of what? Of B. Okay? Now, of course, we say that we can estimate this pi with this value. So because we can estimate this thing with this value, anywhere I see pi, I will put this value we are going to use to estimate. So which means this thing is now going to be, I have my what? P bar in place of this pi. Into here is what? 1 minus what? P what? Bar. Here. Then I open a bracket. N of what? B plus what? N of what? A. All over what? N of what? A, N of what? B. Which means all this thing that is under has been solved to be into this. I will say therefore my zcal equals, what I have here is P of A. So I have P of what? A minus P of what? Of B minus delta what? 0 all over. I have general square root. Here what I have is what? P bar into 1 minus what? P bar, then into what? N of what? A plus what? N of what? B, N of B, all over N of what? A, N of what? B. So this is the formula we are going to use whenever we are not given the value of the population proportions, which oftentimes are not given, and we are meant to estimate it from the sample proportion on the condition that pi of A is equals pi of B. So that is the value we are going to use. Okay? So we now move to the next. I want us to bear this in mind. Where this R P bar is defined like this. Is defined like this. So permit me to clean here. Permit me to clean here. Let us always keep remembering this. The second phase of estimation of the parameters is, or the pi's, is to assume that they are not equal. That's what you're assuming. You are assuming in this condition that pi of A is not equals what? Pi of what? Of B. Which of course is not equals what? Pi. When you have this kind of condition, you go ahead and use your sample proportion to represent your population proportion. Recall that in the first place, we say that our Z curve is given as what? P of A minus what? P of what? B minus what? Delta what? 0 all over general square root of what? Pi of what? A into 1 minus what? Pi of what? A all over what? N of what? A plus pi of B into 1 minus pi of B all over what? N of B. So indeed, if this condition happens, we are going to estimate this pi of A with PA, estimate this pi of B with this. So on that condition, I'll say therefore my Z car now equals what? P of A minus P of B minus what? Delta 0 all over general square root of P of A into 1 minus P of A all over what? N of A plus P of B into 1 minus P of B all over what? N of what? Of B. So this, in this second condition, this is what we are going to do if something like this happens. So these are what we are going to consider when you are talking about the test of the difference between two population proportions. And permit us now to take one question from here and then look at together. So permit me to equally clean this place. Okay, let us try and solve one question together. Solve one question together. That question says, a director of a given government parastatal claims that the proportion of employers, men, who are married is the same as the proportion of women who are married. So there is an employer who is looking at people working under him as strictly two populations: population of men and population of women. But his interest here is that if you're a man, you are either married or not married. If you're a woman, you are either married or not married. And they are making a claim that the proportion of men who are married are the same with the proportion of women who are not who are married. So first of all, we go ahead now to specify what is called our null hypothesis. Null hypothesis here that is saying that H, so I'm going to write solution and we do it together. Is saying that H subscript 0, that my pi 1 minus what? Pi 2 equals what? 0. Yes. That pi 1 minus pi, where I am using pi 1 to represent the proportion of men, so I can equally be using A, so that we can easily use this formula without having confusion. So we go ahead. They say, in a random sample of 290 men, a random sample of 290 men. So my n of A equals 290. In a random sample of 290 men and 200 women, which means my n of B equals 200. 195 men and 113 women are married, which means our x here equals 195 and our x here equals 113 respectively. They say test the claim that pi A is greater than pi B. Test this claim. So the alternate hypothesis H subscript 1, that pi A is greater than what? Pi B. That is the same thing as saying that pi A minus pi B is not equal to 0. Okay? Because you are saying that pi A, you say test this claim that pi A is greater than, which means we say that pi A minus pi B is greater than 0. Sorry about that, because we are talking about greater. At alpha equals 0.05, at alpha equals 0.05. Okay? So they equally gave us a hint. The hint they gave us is that they say that z of alpha, they say z of alpha equals 1.645. Because this alpha is 0.05. This thing implies that z of 0.05 equals 1.645. This is always found using the standard normal table. So what we are going to do is to go ahead and guide ourselves on how to solve this particular problem. Okay? So, of course, in this context, we have stated our null hypothesis. We have stated our alternate hypothesis. We have stated the level of significance. So, what we are going to do now is to go and state the test statistic. And of course, we are not told the value of pi of A and pi of B. So, we must estimate the pi of A and pi of B. But we are going to estimate it now on the assumption that both of them are equal. So what we are going to do now is, we now come here and we say that my z car equals, we are going to use this formula, that P of A minus P of B minus what? Delta what? 0 all over general square root of what? P bar into 1 minus P bar, then into what? N of A plus N of what? B, all over what? N of A, N of what? B, which follows normal distribution with mean 0 and variance 1. Okay? Now we also go ahead. We say where my P of bar is given as N of A, P of A plus N of B, P of what? B, all over N of A plus N of what? B. So we don't know N of A now, we don't know N of B, but we can easily get it from here. So let us come here and get it from this place. So permit me to clean this place I said follows, so we can get our N of A. Of course, our N of P of A is going to be P of A is given as what? X, all over N of what? Of A. And our X here is what? 1, this equals 195 all over what? 290. Then, of course, for us to get our P of what? B, I'm going to have that our P of what? B is given as what? X, all over N of what? Of B, which is, here it is 113 all over what? 200, all over 200. That's what we have. So, of course, for us now to get this value of P now, we now say, therefore, my P bar equals, then in place of what? N of A, I'll write 290. So I have 290. In place of P of A, I'll write multiply by 195 all over 290. We say plus. Here is what? N of what? B, which is 200. So I have 200 multiply by. Then here I have a P of B, and then my P of B is X, and our X is what? 113 all over 200. That's what we have there. And then, of course, when we sort out of these things now, and then we now come back now, and wherever place we see P bar, we substitute it there. Wherever place we see what? P bar, we substitute the value that we are going to get here. Here is my N of A, and my N of A is given as this, we put it here. N of B is given as what? As this, and then we put it here. So at the end, we evaluate this quantity. When we evaluate this quantity, we are going to compare it with our Z, because the given as our Z, of course, is given as what? 1.645. So whatever value you are going to get from here will be compared with this value. If it is greater than this value, you are going to reject P0. But if it is less than this value, you are not going to reject P0. Instead, you are going to accept it. So that is now how to go about this particular question. Permit me to equally give you one thing to try on your own. And that thing I want to give you to try on your own says, suppose that there is a claim that the proportion of men that are hypertensive is equal to the proportion of women that are hypertensive. Full stop. In a random sample of 300 men and 200 women, 192 men and 112 women, respectively, are hypertensive. Test the claim that the proportion of hypertensive men is greater than the proportion of hypertensive women at alpha equals 0.05. And note that your Z of alpha of 0.05 equals 1.645. 1.645. Try to see whether you can use the approach of what we have done here today to be able to come up with something very close to what we have just done. Thank you very much for your audience today as we looked at tests concerning one population proportion and tests concerning the difference between two population proportions. We still plead with you that situation whereby you are learning one or two things from our classes, that you help us share the videos to go viral, like the videos, comment, and equally subscribe to our YouTube channels so that we keep making the scope of our classes to go wider and wider. We also encourage you to stay put for our next class when we should be looking at tests concerning one population mean, tests concerning the difference between two population means down the line. So a lot of questions can come around your way in what we have done today. Thank you very much, and God bless you.